Thank you for coming today. In this session, we are going to introduce the analytical technologies using a supercritical fluid, which can be one of a green analytical chemistry. As you know, the issue of global warming is getting more serious year by year. The main cause of global warming is that carbon dioxide concentration of atmosphere is increasing in Earth. To promote sustainable development with consideration for analysis, it should develop analytical methods that include the ideas of green analytical chemistry. We believe the method using supercritical fluid carbon dioxide can be contribute to achieve it. I'm going to tell why the analytical technologies using supercritical fluid carbon dioxide may give the new method for green analytical chemistry. Before we get into the main topic, let's think about green analytical chemistry. It is an idea that emphasizes the safety of analytical chemistry and the development of eco-friendly analytical methods. Analytical work involves multiple elements. The period engaging the analytical work, the samples, reagent, the instrument, the waste, and the method. If you replace from conventional method to eco-friendly ones, you hope to keep the accuracy and sensitivity, don't you? Now, let us consider what kind of analytical methods that include green analytical chemistry can be used in the analytical process. Analytical process generally consists of sample collection, sample preparation, and analysis. In sample preparation and analysis, organic solvents are commonly used. Focused on the green analytical chemistry, the strategy of solvent reduction is effective. As for sample preparation, from the point of solvent reduction, a microwave-assisted extraction can extract with a small amount of solvent in high efficiency. For analysis, direct analysis methods such as UV and FTIR and gas chromatography can be analyzed without organic solvent. How about HPLC? HPLC is a method using solvent, but it can be also included in green analytical chemistry when it incorporates methods to reduce solvent consumption. As many people know, carbon dioxide with supercritical fluid state has been used for decaffeination and fractionation of chiral compounds. In most of the case, the material of supercritical fluid carbon dioxide that is filled in the cylinders is a byproduct from various industries. Therefore, no new carbon dioxide is produced when we use it for extraction or analysis as supercritical fluid. Although it is difficult to reduce the consumption of solvent used in the sample preparation and analysis to zero, the use of carbon dioxide can reduce the total solvent consumption. In this topic, I'd like to introduce the actual analytical technique using carbon dioxide, which is beginning to be used as a part of green analytical chemistry. Here are the contents in this topic. I'm going to talk about three main areas. Firstly, I will give the properties of supercritical fluid. After that, I will show you the analytical advantage for using carbon dioxide. Finally, I will introduce the examples of analytical solutions. First, I'll give the basic knowledge of supercritical fluid. See a phase diagram of carbon dioxide. Supercritical fluid is one of the states, not a particular compound. A supercritical fluid is generated under certain pressure and temperature conditions, and these conditions are called the critical point. This is the critical point for various substances. Commonly used solvent for analysis such as methanol must be under high temperature to transform to a supercritical state. Water can be also a supercritical state, but it must be placed under high temperature and pressure environment. Methane, ethylene, and propane can be also supercritical state under moderate conditions, but they are flammable and thus pose a safety problem. Carbon dioxide can be supercritical state under relatively mild conditions. Furthermore, it is non-flammable. Next, see the physical properties. The properties of supercritical fluid is intermediate between those of liquid and gases. Compared to liquids, supercritical fluids have a higher diffusivity and lower viscosity and density. An analytical method using liquid as the mobile phase is called liquid chromatography, while similarly, chromatography using supercritical fluid is called supercritical fluid chromatography. The looks of LC and SFC is almost the same, except for the use of carbon dioxide for the mobile phase. You can treat SFC like an LC. There are 3 different points from LC. First, a pump that can accurately deliver carbon dioxide is used. Second, another pump to deliver an organic solvent that is called modifier, which is used for modulating the polarity is used. Third, a pressure adjustment component to accurately pressurize carbon dioxide is required. By adding a pressure regulator to an LC now your own, it can be an SFC system. And you can also use a single system by switching between LC and SFC. Next, I will give the advantage for the analytical technologies using carbon dioxide. Carbon dioxide is used as a mobile phase in SFC analysis. It has some unique properties. Here are typical 4 properties of carbon dioxide using SFC analysis. Let's talk in detail. First, carbon dioxide can vaporize under atmospheric pressure, that is, at lower temperatures and pressures than the critical point. The figure on the left compares the chromatograms of pesticides measured by LC-MS and SFC-MS, and the graph on the right compares the peak area values. When MS is used as a detector, the vaporization reduces the dilution effect of the target component. As a result, the sensitivity may improve when the same MS is used and the same sample is analyzed by both methods. However, that is not true for all compounds. Second, no need to use a hazardous solvent. Carbon dioxide has similar properties to normal hexane. The left is an example of glucosylceramide ceramide analyzed using SFC. For analysis of glucosylceramide ceramide, a normal phase mode is commonly used and chloroform is used as a mobile phase. In SFC, carbon dioxide is used as a mobile phase. So, analysis can be done without using highly hazardous organic solvent. The table on the right shows the result of 6 times repeat analysis of standard solution. Good reproducibility was confirmed for both of retention time and area values. SFC separation has high structure recognition ability. The left shows a chromatogram separating isomers of the glyceride. In SFC analysis, isomers of glyceride can be separated without derivatization. Also, the right is a chromatogram of omeprazole. This is a kind of chiral drugs. In chiral analysis using SFC, chiral chromatography column and carbon dioxide as the mobile phase are used. Additionally, switching from reversed phase to normal phase in SFC is another complicated work. just changing the modifier. The third is its miscibility with organic solvent. Carbon dioxide can be mixed with certain organic solvent, such as methanol and acetonitrile. So, this solvent can be used as a modifier in SFC analysis. Because of this, SFC can obtain a variety of separation patterns. The left is an example of simultaneous analysis of about 500 pesticides. The table on the right describes the physical properties and linearity and reproducibility of some pesticides. When we looked at the octanol water partition coefficient, we can see that it contains high to low polarity pesticides. In this way, SFC can analyze a wide range of types of compounds comprehensively. The fourth is low viscosity and high diffusivity. The left is a comparison of linear velocity and column pressure plotting between HPLC and SFC. As you see the graph, the column pressure of SFC is lower than HPLC. It allows SFC analysis at higher linear velocities. The right is the fundamental plot in HPLC and SFC. For HPLC, the separation performance decreases when the linear velocity of the mobile phase is high. On the other hand, SFC keeps its separation performance even at high linear velocities because supercritical fluid has a higher diffusivity than the solvent used in HPLC. Here is a comparison of HPLC and SFC for simultaneous analysis of tocopherols. The chromatogram above is the result of HPLC normal phase mode, and bottom is SFC. The same separation pattern can be obtained in both methods. And SFC can also deliver the mobile phase at a high flow rate. As a result, we can save 5 times for analysis time. The table below shows the amount of mobile phase used in each method for a single analysis. In normal phase, the organic solvent consumption is 30 ml, while SFC consumes only 0.5 ml of methanol used as a modifier. Reduction of solvent consumption leads reduction of cost. Finally, I will introduce the examples of analytical solutions. As I mentioned earlier, the analytical work generally consists of the flow of sample collection, preparation, and analysis. Analytical techniques involving the carbon dioxide in this flow are noted on the side. Sample preparation involves extraction and fractionation, while analysis involves analytical method development and routine analysis using developed one. In this section, I will introduce analysis techniques related to extraction, fractionation, and method development. First, I will introduce an extraction method using carbon dioxide. This is called supercritical fluid extraction. SCFE enables the extraction of target components without complicated operations. For example, compared to the process of pesticide extraction in agricultural product. Conventional method required pretreatment that involved many processes. In SFE, a sample mixed with a solvent is just placed in a dedicated vessel. Here are examples of the analysis of reduced coenzyme Q10 in dietary supplement. Left is the results of SFC after solvent extraction and right is online SFE SFC analysis. As you know, reduced form can be easily oxidized. In the results of solvent extraction, the reduced form changed to the oxidized. On the other hand, the SFE results show the reduced form has been extracted and detected. Thus, online SFE SFC is very effective for the analysis of unstable compound because it can perform from extraction to separation without any chemical reactions such as oxidation and photodegradation. Next, the fractionation using carbon dioxide. For purification, using HPLC requires post-processing such as evaporation to dryness. In SFC, the post-processing is not necessary. But if the liquid and gas are not separated during fractionation, the liquid will scatter. This is a core technology of PrEP SFC for correcting the target component into the vessel. The gas-liquid separator is needed to separate the liquid from the gas. Various types of separators have been developed by PrEP SFC vendors. By using a fraction corrector equipped with our gas-liquid separator named Lotus Streams, the liquid fraction can be corrected directly into 2 ml vials. Using a fraction corrector equipped with the Lotus Stream, we try to correct the volatile limonene directly into 2 ml vials. The columns of the analytical scale are injected with limonene and the resulting fraction are reanalyzed. In this case, the fraction contains limonene dissolved in ethanol delivered as makeup. The chromatogram below shows the result of reanalysis after diluting this with ethanol. In the interest of time, I will skip the detail, but when I calculate the recovery rate, a high result was obtained. In this way, volatile components can be also efficiently purified by SFC. Finally, method development. This process for SFC is basically the same as HPLC. This is an example of analysis of 3 components using an ODS column with HPLC at the top and SFC at the bottom. Even if the same stationary phase was applied, different separation pattern for HPLC and SFC was obtained. This may bring new separation methods for compounds that have been difficult to separate using conventional method. In SFC method development, different types of stationary phases and modifiers should be experimented as compared to the separation pattern in HPLC. Therefore, a method scouting system that combines multiple columns and modifiers is useful. As an example, here is the configuration of our method scouting system. 4 different solvents can be used to optimize modifiers, and for columns, 6 columns can be used. To conclude my presentation, I'd like to summarize the point. First, the operation of SFC is like LC, except that carbon dioxide is used as a mobile phase. Second, carbon dioxide feature can reduce solvent consumption in the analysis. Third, carbon dioxide can be applied not only to analysis but also to extraction and preparative separation even for unstable compound. Finally, let's review green analytical chemistry again. Here is a reference of carbon dioxide emissions generated during the incineration of 1 liter of the main organic solvent used in the analysis. Organic solvents are incinerated after use, it will generate carbon dioxide. However, the material of supercritical fluid carbon dioxide is recycled gases generated in various industries. Therefore, no carbon dioxide gas emission. Reduction of solvent consumption reduces carbon dioxide emissions as well as cost. We believe SFC can be an analysis method with a reduced environmental impact due to the use of recycled carbon dioxide. Shifting to analytical technologies using carbon dioxide leads to the United Nations Sustainable Development Goals. I hope that this session will inspire you to position SFCs and SFEs as one method of analysis that can achieve green analytical chemistry. That is all for this part. Thank you for attention.
Excellence in science. Shimadzu.